so thanks. First, I thank organizers. Yeah, this is very, as Bobby introduced, this is a very traditional and long continuing series of lecture. And yeah, I myself attended this lecture series as a student, I think a decade ago, plus minus one. And yeah, that was very beautiful memory, and it is my great honor to give a lecture here. Okay, so my talk is titled, my lecture is titled Higher Linear Algebra for Theoretical Physics. So yeah, let me briefly first introduce some main references. So the idea of this lecture is to kind of try to demystify this paper by Davide Gaiotto and Theo Johnson-Fried, titled "The Condensation Higher Categories." And this is a very nice paper, influential, but probably very hard to read for both physicists. So I tried to, I'm not sure I succeed, but I tried to put more familiar context and be explicit about their construction. So that's idea, and yeah, and I will explain later. But a part of my lecture is also heavily relied on this paper by Capucin, Trezero, and Yu, titled "The Topological Field Theory and Matrix Product States." Okay, and I also would like to thank here to the maintainer of the website called NLove, which is Wikipedia for higher category theory, and this is very amazing website maintained by our Schreiber. And yeah, and so many of you probably expected me to talk about generalized symmetry, but I will not. And the subject is very, very closely related to the generalized symmetry, and that's exactly why I learned this topic. But my focus point is not going to be the generalized symmetry. So if you are interested, I guess many of you, then you can refer to, well, there are many lecture notes by now in the archive, but since this is ICTP lecture series, so I will mention the Sakura's ICTP lecture last year. Okay, so any question about so far? Fine. Oh yeah, so I repeat, Bobby, that it is very, very important to ask questions, and so, and maybe particular for me for my lecture, because I'm going to, I mean, you might expect that my lecture is going to be very math oriented, and so there can be like some terminologies, just a terminology problem about, yeah, I heavily use the math terminology, and you might not, but you might just ask, okay, then yeah. Sometimes it just takes like five seconds to explain, so then it will help everyone to understand the lecture. Okay, so let's start this lecture. So higher linear algebra. So I think I don't have to explain how important linear algebra is, and in particular in the quantum mechanics, if you learn in the undergrad about the quantum mechanics, then you effectively always doing linear algebra in one way or another. So that's very important, and very excitingly recent development in the interface between math and theoretical physics is the emergence of this higher linear algebra. The concept of it itself is bit goes back to, I think, at least to the Bayes and Crowns in 90s. But recently, really, there's a big progress has been made. And I predict that this is going to be very important in the field of quantum field theory. So the higher linear algebra is supposed to be the linear algebra for quantum field theory, and or more broadly, some quantum physics defined on space-time, not just the arbitrary quantum mechanics. So in other words, the locality of the space-time is built in a way in this thing. Okay. So what is it? So good working definition of higher linear algebra, or maybe conceptual definition, is just this is just a synonym of TQFT. So that's one good way of thinking about it. So this higher linear algebra comes with a degree. So let me call the P linear algebra. Then that's corresponds to P dimensional. Yeah, this is the space-time dimension. Okay. So P equals to 1. One linear algebra should be linear algebra. And then corresponding to 1 dim, this means 0 plus 1 dimensional TQFT. Well, it's maybe topological quantum mechanics. And what is this? So I said it's topological. And in this dimension, this means that Hamiltonian is 0. Okay, so Hamiltonian is just 0, and the other portion of information you can have about this kind of quantum mechanics is just that you have a Hilbert space. This is a state space. So it's just topological quantum mechanics is just a synonym for the Hilbert space, and that fits with this kind of paradigm. Okay, and so conceptually, in the higher linear algebra is just replacing this to the more TQFT in higher dimensions. But the main point that I'd like to emphasize here is that it is not just a synonym and or some another name, but it is really a linear algebra. So of course there is a reason that people want to call it a linear algebra, and I'd like to explain that. Okay. Yep. Where's the? But where's the erasers? Oh. Now, let me think. Yeah. So in this lecture, I'd like to be a bit more precise about this TQFT part, and I replace this. I mean, this is just a conceptual thing, and there's a room to wiggle with this part. So as a working definition, I rather use here the P and MPS is a matrix product states. I will explain. If you know about it, the one MPS is MPS, and sorry, there is a discrepancy. This is not P minus 1, and I should say fixed point. Yeah. Also, I failed to ask that but I'd like to know that that the background of you guys. So would you raise your hand that if your field, so depending on the archive prefix, so the primary, what is your primary archive category? So is it the HepTH? Yes, HepPH. Many, and HepLat. No, CondMot. Okay, good. Okay, so yeah, this is supposedly the spring scale for the string theory, so that's what I expect. Yeah, but sorry about that. But I'm going to be more CondMot style in this lecture, and that's is because that's so the matrix product state is a concept in the theoretical condensed matter physics, and that is very useful here. Okay, so I will explain about that. But before that, maybe I also give you some kind of, well, I'll leave it later, sorry. So let's start. Let me start from p equals to 1 case, though. Then I'm going to then this paradigm I should be talking about 0 MPS, and what is 0 MPS? Okay. So p equals to 1. And here, by 0 MPS, I mean some 1 plus 0D topological chain. So this is some one-dimensional classical statistical mechanics model, and that is topological. So let's think about the one-dimensional chain, and I draw in this way. Here, n is just a set of variables, runs through 1 to n. This is just a set of and the so here I put the variables at the edge. You can of course think about the dual picture that you have variables lives at each site, and then you put the W is the Boltzmann weight. sure about the spelling of Boltzmann's weight. Okay. Oh, yeah. Yes. So I'm thinking about a homogeneous chain, and I put the same weight. Yes. Okay. So the partial function is just that okay. So, yeah. And well, of course, you can regard this as a matrix. So this is just and if you make it this periodic, then it's just a trace. Okay. So now this thing depends on the length in general. And topological, by topological means that in particular, I don't want this topological chain to be depends on the length. So I demand independent. This partial function is independent of the length. And this gives you more locally, I demand that you can fuse the two weights into one and then get the same. So W squared equals to W. Just says that W is a projection. Okay, good. Now, okay. So let me call this rewrite W as a P because it is a projection. Okay, so then my claim is that this is corresponding to doing a linear algebra and what I'm doing now. So to see that part, I raised the main philosophy. Maybe I put the main philosophy here. Okay, so the main philosophy is that we want to do P linear algebra or like P vector space. And that should correspond to P minus 1 MPS. And this P minus 1 MPS also corresponding to P-dimensional topological system. here I'm doing P equals to 1 case, so I'm talking about the one-dimensional topological system. And okay, so if you have a vector space, then you should also be able to think about the vector itself. This is the element of vector space. And that should correspond to the boundary condition, topological boundary condition of this. Okay, so in this equation, yes, I'm going to talk about the more general boundary condition. Okay, so boundary condition. Yeah, sorry. So this is periodic. Boundary condition, you just put another weight at the end. Okay, and this is just a vector. Okay, this is in the C to N. So this is S boundary weight. Okay, and I want this to be also topological, meaning that this boundary condition absorbs the bulk weight. Good. Now, in other words, this BL is an eigenvector of W, or I rewrite it to P with eigenvalue 1. Okay? So from this philosophy, I'm proposing that this topological boundary condition should be considered as a vector in the vector space corresponding to this topological system. So what is that vector space in the traditional sense? And that's where this BL, the topological boundary condition, lives. So here, this topological chain, the classical chain that specified by OP. The number of variables and projection. This is in the matrix and N by N matrix. This corresponds to image of B. Then the topological boundary condition lives in this. Okay. So P here, the P, of course, P squares. The projection. Okay. So it's kind of a contrived way of, or maybe tautological way of defining a vector space. But yeah, here, like P is already a matrix, so it looks like a tautological, but this P, this image of P doesn't have necessarily the canonical basis, while this P this be acting on, of course, on the C to the N, but that's defined as a like explicit tensor product. Here, the image of P is more abstract vector space. That's the thing. And okay, so I'm doing something trivial here. So
I have a question.
Yes.
So do I understand correctly that here there are two numbers? One is n, the total dimension, say, and one is the dimension of the image of P, and they're not necessarily the same.
Not necessarily the same.
Okay, thanks.
Yes.
The relation between the topological chain and in the case of P equals 1, a vector space is, you are saying the vector space is the image of P?
Yep. Not this. Not this ambient one, but image of P.
Okay. And what are the vectors?
So vector is an element of image of P. Also, yeah, so because P squared equals to P, the eigenvalue of P is either 1 or 0. So the element in the image of P are the eigenvector with eigenvalue 1, and that defines a boundary condition, the topological boundary condition for this chain. And this is I'm saying this because this kind of contrived definition goes up to the higher dimensions.
But in particular, for any projector, you can define, there is a one-to-one correspondence between projectors in general acting on Cn and topological chains. And there are no more topological chains in 0 plus 1 than in P, for any P?
In this dimension, by this definition, almost tautologically that is just specified by the projection matrix, yes. Okay. Now, if you are doing linear algebra, then we want to talk about a linear map. And that's, maybe I should write there. And linear map corresponds to the topological interface. Okay, so suppose that you have two topological chains, N1, P1, and N2, P2. Okay, so you have this, and the other side you have that. And then let's say we have some interface. Okay, so this is F. You have N1 here, N2 here. F is in the matrix, just by definition, is in the matrix of N1 times into some rectangular matrix. And then, again, we want the topologicality. So topologicalness. Okay, so F topological. Is, again, this F can absorb either P1 or P2. So P1 F. Oh, yeah, here think it should. Sorry, here absorb is not correct. It's we can let me write. So topologicalness means that I can move this f. So and these are the same. Of course here. And these are the same. Okay, so this means this equation. Yes. Sorry. Oh, yeah, this is a local move that makes you, okay. So in a continuum drawing, here you have some one-dimensional system, and then you have some boundary condition. And then this equation is like you can shift this boundary by one side. So it's like you can move this into shrink it, or you can go in the other way. Yeah, and the topologicalness means that everything that shouldn't depend on size. So yeah. So in the same picture here, this is like in a continuum picture. You have an interface between two systems, and you can move this interface in either way. Yes.
Also, when you're specifying the topological chain, you give me n, you give me the matrix P, but shouldn't you also give me the boundary conditions? Because is it clear that there are no degeneracies in the one unit eigenspace of P?
Oh yeah. So in general, this P can have multiple eigen vectors with eigenvalue 1, and we want to think about that case because to think about the multi-dimensional vector space. Yes. Yes.
So to define the chain, we need the projector and the boundary condition, right? And we are assuming that we only have one boundary condition, or can we have two?
Oh yeah.
Two ends.
Thanks. So of course, I only talked about like the column vector, but you can also think about the row vector. So there's also right boundary condition, and then we demand this to be topological in this way. So then that's the row vector with eigenvalue 1.
So to define the chain,
Yes.
we need two vectors, right?
Yes. So thanks for that question. So so with the open chain, it's like R BL. This is the partition function. But then we demanded these two, so it's just product, or the pairing of the two boundary conditions. Thanks for the question. Yes, you're right. Yeah. Periodic. You can. Yeah. Again, this is trace of 1. But if you pick a basis, then basis of image, then you can put well, actually, well, and this is this dimension of image. Okay. Thanks for yeah. So if you only demand this, W survives. I also demand this thing. So the last one can be absorbed.
Also, one question on the F. So, is the fact that F is topological, do you have to demand it additionally to the chains being topological, or does it always follow that F is topological if the two chains are topological?
You have to. This is additional demand. Yeah. Obviously, this doesn't hold for any rectangular matrix. So this is additional constraint for F.
Thanks.
To be topological.
Maybe as a follow-up, I mean, it's a constraint on F generically, but in a chain, isn't this condition just satisfied by, because I can add and subtract P1s and P2s by the topologically condition on those? Because P1 and P2 are both projectors,
yeah, so
right?
that's the same question as similar question as before. That if you have in extreme case that you might not have. Let me see. The question is that yes, so we can always for any F that any F, then we can think about F twiddle is P1 F P2. Then this F twiddle satisfies this condition because P1 and P2 are projectors. Yeah, so we can say either way that we want to consider F satisfying this, or we want to consider F, but then anyway we multiply P1 and P2 from side by side, and yes. Sorry, F.
Shouldn't you also demand that FP2 should be equal to F?
Do I demand this?
Yeah, because you can shrink the boundary, you can shrink all the boxes to the boundary.
I don't. Okay, so one way, going back to boundary case, is that this thing happens to be N2 equals to 1 and P2 equals to 1. In other words, the boundary is a interface to the trivial system. Then this condition that becomes yeah. From I think it's intuitive from this continuum picture that if you have the other side, the other thing attached to here, then this is what you want, and so. But anyway, of course, you can also shrink this side. So that's also possible, yeah. But the topologicalness itself on the interface, if you don't assume that these two sides are not topological, then you want this. Okay. Yes. Yes. So Yeah, what I'm claiming here is that this kind of F with this is in one-to-one corresponding to the linear map from image of P1 to image of P2. Yeah, and of course, to any two vector spaces, there is a non-trivial linear map. If one side is non-zero, both sides is non-zero. Okay. Yeah. So that what I said, that this thing, this means that actually that F goes to M. You can regard this as this is a linear map. Good. Anything else? Sorry, yeah. Well, if n1 equals n2, but the P1 and P2 can be like the number of eigenvalue with eigenvalue 1, eigenstate with eigenvalue 1 can be different.
Yes, I know it's a little bit inconvenient, but please wait for the microphone when you ask the question. Otherwise, the other people cannot hear your question. Thanks.
Yeah, thanks for those people asking questions. It's so far very engaging and very happy. Okay, and what to say? So I have like 20 minutes left. Well, a few things to say. One thing is that the reflection positivity. Okay, so that's that. So you have chain. And let's say that you put the same boundary conditions on left and right. And here, the same means that, of course, same as the vector in C to the n. Okay. Maybe I write explicitly that BL and BR is. Or maybe tan. That's a better way of. No, sorry. I think I made a mistake somewhere, sorry. Sorry. Let me say this. Not the same. But then we are thinking about flipping the two sides. So then you have no. Sorry about that. explanation is here. So sorry. If you put the same, then this is kind of BB. We are doing BB. Then we want this to be positive. This is a refraction positivity. This inequality comes from that if we want to think this topological chain system is actually the Euclidean version of quantum mechanics, and then if you think this as actually this is a time, and we are really taking inner product in the topological quantum mechanics, then of course we want this inner product to be positive. So, and this demands that P and is actually the orthogonal projection. So if we demand a reflection positivity, then or to have this resulting image of P, so then this image of P has Hilbert product. Yes.
So you said that this is the Euclidean version of the topological quantum mechanics.
Yeah.
Then can we define the unitarity or non-unitarity of that Euclidean version of Euclidean topological quantum field theory by this properties or something? Can you define the unitarity or non-unitarity?
Oh yeah. So that's the yes. So yeah, that's called what's called a reflection positivity, and that's basically saying that in this case you have this interval, and we regard this as a time, and then if this configuration is reflection symmetric, so if we do refraction, refraction in this dimension is just flipping the dimensions. But in any dimension, you pick the direction that you call time. This is Euclidean, so you can pick arbitrary direction and you call it time, and then reflect. And then if this system, the configuration is reflection symmetric. In other words, So if you flip, then you get the same diagram. In this case, just the two boundary conditions are the same. Then you demand the positivity. So that in this case, the Z is. So as evident here, that the idea is that if this is really the Euclidean time, and then you pick cut at the middle, and then this is some inner product with this. Even if it's not topological, that this thing defines a vector and defined on this. So some vector, and you are taking inner product. And that's if the system is unitary, then you want the positive inner product.
If that is violated, then can we say that topological quantum field theory is non-unitary?
Yeah. Well, it's more like a definition, yes. Yeah.
So originally, the space of chain corresponds to 2 times the image of P, right? Because you need 2 vectors from the image of P to define a chain. But the space of chains that have a Hilbert with an inner product is 1-to-1, right? From vector to chain.
Sorry, question is, oh yeah, so here you're asking that whether this inner product is uniquely defined on this space. That's
No,
your question?
that to define a chain,
Yeah.
you needed 2 vectors, the 2 endpoints, right?
Oh, yeah, on open space, yes.
Right.
Yeah.
But to ensure that the image of P has a Hilbert space, you need that 2 endpoints are the same.
Yeah,
right?
so that's, I mean, what you demand is this, right? If you the same boundary condition, then I mean, inner product with the same vector, you get the positive number. That's what you expect for the Hilbert space.
Okay.
And okay, and yeah, so the inner product is just induced from C to N. We have a canonical inner product for the C to N, which is positive, and if we demand that the projection is also orthogonal, then you can show that the induced inner product on its image is also positive. Okay. Sorry about the not well prepared about this part. And okay. So any other questions so far? Yeah, last comment is that well, I'm not sure this is useful, but so here, what we did is starting from C to N is the number of variables, and then you put the orthogonal projection, and we get one vector space, which is image identified with image of P. And this is also Hilbert space. If P is orthogonal, then this is a Hilbert space. Good. We have canonical basis here, because this is explicitly defined as a tensor product, direct sum for each variable. And then, so then we have let me call, maybe I put tilde here, and let me call this. Okay. And then this thing is not the basis in general. Of course, you have n of vectors, and then you get n of vectors, and the dimension of image of P can be smaller than here. Now, however, you can show, or easily show, that it's still, this is just a remark, by the way. On in P. So this is just, yeah, because from this construction it's evident. And yeah, and this kind of span, and also of course also EI spans. Well, it's obvious. Yeah, I don't write it, but yeah, this kind of the set of vectors that specify satisfying this relation is called possible framing. And so this setup of like regarding and any possible framing, the set of vectors satisfying this relation, it comes from this construction of having an ambient vector space and project with an orthogonal projection. So that's a Naimarcus theorem about framing. And yeah, so this topological chain reconstruction of Hilbert space is also naturally gives you the possible framing. This is just a comment. Okay, so any questions so far? I'd like to recap that so we
Sorry, I'm a bit confused about your resolution of the identity. So you're taking a basis in Cn, and then you're projecting it out. So EI ket is in the image of P, right? So then the resolution of the identity that you've written down should be in the image of P, right? Or am I confused?
Oh yeah, sorry, yeah. Okay, yeah. So far I was doing almost trivial thing and just explaining that this philosophy of like P vector space it corresponds to P dimensional topological system at the P goes to 1. Yes.
So maybe it's about motivation. The idea is there any physical system which you can relate to this topological chain? Zero plus one dimensional. The idea is you are trying to construct an algebraic structure by using physics, or I'm a bit confused on what could this represent in terms of a physical system and where are you going to?
Okay, yeah. So thanks for that question. That I have to really explain that. So yeah, in this dimension is of course a bit too trivial, and going up, then there is going to be more interesting systems that at least many theoretical physicists, including in the condensed matter physicists, are interested in. At this dimension, I don't claim that this is terribly interesting physical system. Other than that, yeah, if you regard this as just a Euclidean version of topological quantum mechanics, then topological quantum mechanics is okay. So I should have said that. So topological quantum mechanics is you can think of the IR limit of quantum mechanics, meaning that you can only look at the ground state. So, I mean, in general, you of course you can have a non-trivial Hamiltonian in quantum mechanics, and which has non-trivial eigenvalues. But then, like in the deep IR, that you don't have any energy to excite the states, then you only arrives in one of the ground states. That's the IR limit, and this is yeah. So this is kind of the long range. Yeah. So this is you can think of this as some long range limit of some statistical mechanics system to 1D chain. And that's going to be the important also, like to regard these topological systems as the IR limit of some gapped system. Thanks for the question. Any other questions?
Yes, sorry. I have a question I don't understand well. You have this subspace that is the image of P, and with the chain you associate an inner product to that space. And modifying the boundary condition, you have the difference the different evaluations in the vectors. Is that the idea? And so the chain gives the inner product if
yes.
they have a reflection positivity.
Yeah.
Is the idea?
That's the idea of this word. Yes. Yeah. So okay, yeah. The reason I explicitly explaining this is that, of course, this is kind of trivial in these dimensions, but the higher dimensions is still, I mean, it's very recent development to understand what is the true reflection positivity in the higher dimensional TQFTs. And so in this, but yeah, in this language, I believe that like working in very explicit way, then we can see that what we should demand for as a reflection positivity slash unitarity for the higher dimensional topological systems. Any other questions? Okay, so I'm supposed to finish in 2 minutes, but there were many questions. So let me start talking about p equals to 2 case, which is more interesting. And oh, including questions. Yes. Yeah, I know. Yeah. So yes. So p equals to 2 case, and that's, as I announced, that should correspond to the fixed point MPS. And so I direct to site. I already wrote here, but again, it's paper couple centuries. So sorry, no, y. And okay, so the MPS matrix product state. And to get the matrix product states, I repeat almost the same drawing. But then here, it's better to, well, then I still use the red W. And here, okay, so essentially I just put the additional vertical arrow for each box. And this defines here, sorry, the W here is not just a weight. It's a linear map from H to sub B to the linear map. And then we can contract. Oh yeah, so here we've already unlocked the knowledge of vector space. So from now on I just use the freely use the knowledge of linear algebra. Okay, so that's another philosophy that we go up step by step. So to build p dimensional linear algebra, that we use p minus 1 linear algebra. Okay? So here I can use the usual linear algebra to define the two linear algebra. Now, so what does this picture gives? And this picture gives me to some state. Okay. Let me write as this is a circle. This is backslash, and this is okay in H2. If you have n of them, and do some. Okay, so that's the, and this is called the MPS. If we expand this W as like basis of possible framing, we expand it as AIJ H. H A I B. So if you pick a basis for each vector spaces and expand it, then you have this tensor, and then this thing state explicitly is, oh, sorry. I decided to make the Bura. Sorry. So this is on in star. And yeah, sorry. This choice was yeah. Sorry about talking about the Bura instead of cat, but that's going to be easier for me. Then we just contract like
What is I and what is J? I cannot distinguish.
yeah, okay, so good. Here should be J. So A is the index for H, I and J are index for V. And then here, the Bura state, we get and trace of W. This is by periodic boundary condition, and this W upper script of maybe lower script. Sorry. Okay. So this W lower script A is the matrix acting on V. I might be messing up I and j. Please correct. And this and the end is an endomorphism. An endomorphism linear map of B. It's just matrix acting on B. And so each fixed A is the index for H. For each fixed A, I regard this thing as a matrix acting on B, and then I multiply these matrices, and then so I get some number, and then I construct this vector in the product here is space. That's what this picture gives you. That's the matrix product state. Any questions so far? So then, yeah. Any question? Yes.
So for p equals 1, I knew what a vector space is, so I knew what I was expecting to have vectors and a vector space.
Yes.
For p equals 2, I don't know what a two-vector space is.
Yes.
I don't know what we're expecting to have. Is that a definition for a two-vector space?
No. So this is just a definition of matrix product state. Then I am going to define the analog of topologicalness we talked about in p equals 1 case. So that's going to introduce a fixed point MPS, and that's another additional structure. And from that structure, we can define the topological p equal two-dimensional system, and that is the two vector space.
Just a question about notation. So this circle over W, it means that the chain is periodic?
Oh, yeah. So, no, this is just, sorry, maybe just confusing notation. It's just, this is a kind of composition, right? This is a, W is a linear map, and you compose this part, and leaving that part.
Sorry, what was the step that you did from W to the bra, W N?
Sorry, W2?
Yeah, what was the step from going to that line to the last line? What is the step, what is the calculation step from this line to this line, yeah?
This thing. Yeah, so that's, this is just a literal expansion of this picture. And so each W, you have tensor assigned to each box, and then this line means that the contraction of the index. So yes. So maybe just one box. You have index A here and I here. This is this clear? Yeah, I mean, more explicitly I write. You have, yeah.
we're working with periodic boundary conditions once again, with all the traces.
Sorry, yeah.
So we're working with periodic boundary conditions once again because you have traces.
Yeah. The periodic boundary condition gives you, it gives you trace. You can also have a open chain. Then yeah, you can also have definite right boundary conditions. Okay. So yeah, I'm finishing. So next, like in the afternoon, I guess, I'm going to introduce the fixed point MPS, and that's a way to compress this chain into a smaller chain. Okay? But demanding too much, then you get something trivial, or just a usual vector space. So there is a I will talk about it. Yeah, so if you want to know the answer in your head, that we will arrive on something called the special symmetric covariance algebra. That is a two-vector space. So that we will see. Yeah, so I finish here. Thanks for the listening.